Good afternoon, everyone. I hope you're well and had a good weekend. This lecture is the third in a set of 6 we have for PM1B, looking at some of the core chemistry concepts you need to understand pharmaceutical design. In this lecture, we will start to look at stereochemistry, the shapes of molecules. The recommended textbooks for these 2 lectures are the same as for the first lectures in this set. Chapter 3 in Jurek describes what we'll be looking at today, although do note, as much as it breaks my heart as someone who works with carbohydrates, we will not be looking at conformational isomerism in these lectures. So we'll be spending 2 lectures looking at the shapes of molecules. And by the end of these 2 lectures, I hope you'll be able to understand the importance of 3D structures and the connectivity of atoms within drug design and synthesis. Define and understand the terms isomer, constitutional isomer, and stereoisomer. Define the terms chiral, achiral, enantiomer, distereomer, racemate, and mesocompound. Assign the stereochemical descriptors R and S, E and Z to the appropriate molecules. So let's start with a quick recap of what we did last week. Last week we started to explore how we could bond atoms together to form molecules, and we looked at how carbon could form hybrid orbitals. We worked out that if carbon is bonded to 4 other atoms, it is sp3 hybridized, as in ethane. If it's bonded to 3 other atoms, it's sp2 hybridized, as in ethene. And if it is bonded to 2 other atoms, it is sp hybridized, as in ethyne. So these hybrid orbitals can give rise to different shapes and different molecular geometries. And you can see how atoms in these molecules would be arranged in 3-dimensional space here. The bonds around each carbon atom are arranged in a tetrahedral fashion in ethane, a trigonal planar fashion in ethene, and a linear fashion in ethyne. Now you'll find that chemists use lots of different ways to describe molecules depending on what they're trying to communicate. Now these drawings are examples of structural formula. A structural formula indicates not only the number of atoms, but tells you a little bit about the connectivity of the atoms and sometimes their arrangement in space. A molecular formula, on the other hand, consists of chemical symbols for each of the constituent elements, followed by numeric subscripts describing the number of atoms of each element present in the molecule. Molecular formulas are compact and easy to communicate. The molecular formula for each of these compounds is shown on the right-hand side of the page here. For ethane, it is C2H6, so 2 carbon atoms and 6 hydrogen atoms. For ethene, the formula is C2H4, so this molecule is built up of 2 carbon atoms and 4 hydrogen atoms. And the molecular formula of ethyne is C2H2, 2 carbon atoms and 2 hydrogen atoms. Take a few minutes to draw out the structures below and work out the molecular formula of each of these compounds. This slide contains the answers to the exercise shown on the previous slide. Now, molecular formula are all well and good in telling us about the number of atoms in a molecule, but unlike structural formula, they don't tell us anything about the arrangement of atoms in a structure. As an example, there are many possible structures with the formula C6H12. Take a few minutes and see how many you can draw. Remember the rules for connecting atoms together. Hydrogen can only be bonded to 1 other atom, whereas carbon can share electrons to form 4 bonds. There are many possible structures with this formula. Some examples are shown on the right-hand side. You'll notice that some of these structures are cyclic, some of them have double bonds, and some of them have branches. Molecular formula don't tell us anything about how the atoms would be arranged. The structures on the previous slide all have the same molecular formula, but the atoms are connected in a different order. It's almost as if I gave you a number of Lego bricks, and the isomers are all the different ways you could link these bricks together. Same number of bricks, but connected in a different order. They're constitutional isomers, and you might have heard them referred to as structural isomers because the two terms are often used interchangeably. But this is a key definition. Constitutional isomers have the same molecular formula but a different connectivity of atoms. They are joined together in different ways. The two structures on the left are examples of constitutional isomers. Both ethanol and dimethyl ether have the same molecular formula, C2H6O, but they are very, very different. Ethanol and dimethyl ether behave differently. Ethanol has a boiling point of 78 degrees centigrade. Dimethyl ether has a boiling point of minus 24.8 degrees centigrade, so it's much lower than ethanol. And this type of observation is common. Constitutional isomers have very different physical properties. They're very different structures after all. Likewise, they have very different chemical properties too. If I take sodium and throw it into ethanol, it'll react. It'll form sodium ethoxide, this compound here, and it will give off hydrogen gas. But if I throw sodium into dimethyl ether, nothing happens. So as well as having different physical properties, constitutional isomers often have very different chemical properties too. So as the complexity of the molecular formula increases, i.e. we get more atoms to play with, the total number of possible isomers increases. Take a look at these examples. There are only 2 possible isomers of C4H10, but there are 3 possible isomers of C5H12. Another example of constitutional isomers are the xylenes, dimethylbenzenes. These are benzene rings bearing 2 methyl groups. These methyl groups can occupy different positions on the aromatic rim. We often refer to this as positional isomers. So your turn now to do some drawing. Can you work out how many possible isomers there are of a compound with the formula C6H14? I'll give you a hint. You can either have 4, 5 or 6 structures. How many can you draw? There are 5 possible isomers here, and the structures are shown on this slide. Now do be careful if you're asked to draw these to check that you haven't drawn the same structure more than once. It's very, very easy to do. So constitutional isomers can be incredibly different. They can have different functional groups. They might have the same functional group in a different position, or they could even have the carbon backbone drawn in a different way. Constitutional isomers are one possible type of isomer. Isomers we get if we rearrange the atoms in a molecule and connect them back together in a different order. But there are other types of isomers as well, those where we have the same connectivity but the atoms are arranged differently in space. These are referred to as stereoisomers, and there are 2 broad classes here, enantiomers and diastereomers. Stereoisomers occur when molecules have the same molecular formula and the same connectivity of atoms, but a different arrangement of atoms in space. So how does this occur? Well, it's probably easiest to think about this by talking through some examples. So let's start by looking at how atoms are arranged in space in a molecule which has no isomers at all. So this is methane, which we've met many, many times during these few lectures. The carbon atom in methane is tetravalent. It has 4 single bonds attached to it, and it's sp3 hybridized. You'll notice though that we've drawn these bonds, even though they're all the same, in a slightly different way. These 2 bonds here are shown as straight lines, and this shows that they're in the plane of the paper. This bond here has been shown dashed, and that tells me that it's pointing backwards. Whereas this bond here is shown as a wedge, and it's pointing forward. And this is what it looks like if we draw out methane as a 3D model. The bonds pointing backwards on this structure we show drawn as a wedge, and so on. Well, that is all well and good, but methane doesn't have any isomers. So if I made a molecular model of the structure and rotated it, it'd look the same whichever way I turned it. But that doesn't hold true for compounds which are more complicated. Look at the structures shown below. These are all isomers of menthol, which can be extracted from peppermint oil. They're all the same structure in terms of atomic connectivity, but you can see that some of the bonds are pointing backwards, whereas others are pointing forward. So in menthol, this bond points backwards and is shown as a dashed bond, whereas these two bonds point forwards and are shown with a wedge. This structure, neomenthol, on the other hand, has bonds pointing in different directions. And there are differences in the direction these bonds are orientated in space in all of the other structures too. Now we've mentioned before that stereoisomers occur when molecules have the same molecular formula and the same connectivity of atoms, but a different arrangement of atoms in space. And there are two main types of stereoisomers, diastereomers and enantiomers. Enantiomers arise through the fact that it's a fundamental property of some compounds that they have non-superimposable mirror image forms. The example that we always use to show this are your hands. They're both hands, of course, but if you try putting your left hand into your right glove, you'll soon see that they're mirror image forms. We use the term chiral to describe this. So your hands are chiral, in the same way some molecules are. So we can define an enantiomer as a class of stereoisomers that are non-superimposable on their mirror image form. Amino acids are a particularly good example here, so let's start by looking at alanine. The carbon marked on the diagram is sp3 hybridized and is tetrahedral, so it can have 4 bonds attached. In alanine, we have an amine, a carboxylic acid, a methyl group, and a hydrogen atom bonded to this central carbon. So if we change the way that 2 of these bonds are facing, we can draw structures which are still alanine, but they can't be superimposed upon itself. So enantiomers are stereoisomers that are non-superimposable on their mirror image, and all that is required for a molecule to be chiral, to have enantiomers, is a tetrahedral carbon which has 4 different groups attached. Can you spot the special carbon atom in these structures? All of them are chiral. So enantiomers are stereoisomers that are non-superimposable on their mirror image, and we know we can spot where this might happen by looking for carbon atoms in structures with 4 different groups attached. Look at the 2 molecules below. Find the carbons with 4 different groups attached. And they're highlighted in red on this structure. So although these compounds might look very similar, stereoisomers are particularly important in biology. Molecules have shape, and stereoisomers have different shapes, and this can be very important in the binding to receptors and biological targets. 2 good examples here are the stereoisomers of limonene. One non-superimposable mirror image form smells of lemons, whilst the other smells quite strongly of orange. Likewise, the molecule underneath. One isomer of carvone smells of caraway seeds, whereas the other smells of spearmint. So in this lecture, you started to explore the concept of 3D structures and the connectivity of atoms. We've introduced the concept of isomers and have looked in detail at constitutional isomers. And we've started to explore the concept of stereoisomers and how atoms can be arranged in space.